Hello again. We are looking at integrating powers of trigonometric functions once more. In this video, we will look at some special cases. Many cases do not follow the specific patterns that we have shown in cases 1 to 5. In particular, odd powers of secant and even powers of tangent have to be handled differently. Here is a sample of such examples. For instance, tan square of x is an even power of tangent. It has not been covered in cases 1 to 5. This is actually a straightforward integral because tan square x can be replaced by secant square x minus 1. Both secant square x and minus 1 are basic integrals. The task is a little bit more complicated with tan of x to the power 4. However, the same approach might actually be helpful. Let's suppose we break up tan x to the 4 into tan square x's and use the same trig identity as we had before, where tan square x is replaced by secant square x minus 1. Then, expand this binomial term into secant x to the power 4, 2 secant square x's, and 1. The last two terms are actually basic, and the first one is an even power of secant, which we have discussed in case 4 itself. We will split up our integral into 3 separate integrals, seeing as we need not use techniques for the second and third of these integrals. In the first integral, our strategy was to pull out a secant square x dx along with the dx to use a trig identity that replaces secant square x by 1 plus tan square x, and then recognize that the derivative of tan of x is secant square x, and therefore proceed with a substitution. The end result is a power rule that can be applied to the first integral and basic integrals to the second and third. The first integral is solved by the power rule. The second and third are basic. And recalling that u actually stands for tan of x, we can go back to our original variable. In this final result, there are like terms that can then be regrouped. Example number 3 now involves an odd power of secant. It seems pretty simple, but secant x dx has no basic antiderivative and no specific technique to be solved with. However, this integral becomes quite simple if you chose to multiply above and below by secant x plus tan x and divided by secant x plus tan x. Now, of course, Marco in the back right now is saying, but sir, how would we have known? Oh well, that's why we go to school. Now distribute secant x to the numerator's terms. Secant square x plus secant x tan x just happens to be the individual derivatives for tan of x and secant x, which you actually recognize at the bottom. I'm going to pull those numerators expressions out, and then just recognize that a substitution will actually fulfill the roles of the u, the denominator, and the du, the terms that have been separated. 1 over u du is a logarithm, and in this case we've skipped the step of using u's antiderivative and went straight to x's. I suggest you add the integral of secant x dx equal ln of secant x plus tan x to your basic list of formulas. Here's example number 4, where we have odd powers of secant. In this example, we've chosen to split secant square x dx aside. However, unlike in case number 4, where this is meant to be a du, this time no substitution will make that du correct, because there is no u equal to tan of x to work with. Instead, we're going to proceed by integrating by parts. The first of these terms, secant x, can be designated as f because we can differentiate it, and the second term, secant square x, can be identified as g prime because we know how to anti-differentiate it. So leaving secant x become f, f prime will be secant x tan x, choosing g prime to be secant square would make g equal to tan of x. Here is what integration by parts has produced. We have a term, secant x tan x, that needs no more integrating. We have a new integral with secant x and tan square x dx. Unfortunately, this is neither an even secant nor an odd tangent case that we saw in cases 5 and 4. And therefore, we're stuck improvising again. As a leap of faith, suppose that you were to replace tan square of x by its trig identity secant square x minus 1, and then expanded the terms. Now, what we do notice is that a boomerang effect has taken place, and the integral secant cube x dx has come back to what it was in from the onset. Therefore, we can regroup the common integrals of secant cube of x on the left, and then finish our integration on the right-hand side by recognizing that the integral of secant x is the example that we did just previously, and for which you now have a basic rule, which is ln of secant x plus tan of x. You can then isolate the integral of secant cube of x dx by dividing both sides by 2, and by adding an arbitrary constant. In many situations, if you see no other alternatives than the examples we've covered so far, you can try to convert all expressions into sine and cosine. For example, tan square of x over secant cube of x does not fit with any of the cases 1 to 5. We can, however, replace tan square of x by sine square over cos square, and if you remember that a secant is 1 over cos, then dividing by secant cube of x is like multiplying by cos cube of x. Coses are now common and can be simplified, leaving secant square x cos of x. And now a substitution would fit perfectly.